Okay, anybody have any homework questions?
Question, because we only have one.
Oh, yeah, right. Well, you could have multiple questions about one thing, like why did you do this to us, etc.
I ask myself.
Yeah. Why have you done this to us? Okay, well, I'm just going to go back to the example problem we were doing, and then we'll do more example problems. Okay, so we had an equilateral triangle with pin joints at those three spots and a force of 600 newtons. And the masses were 20 kilograms each. And I numbered the members 1, 2, like that, and I named the joints A, B, C. And we already went through the free body diagrams. And so remember that the thing is, you can do this perfectly fine, treating the pins like separate bodies, or whatever joint you're dealing with, treating it like a separate body. But it just brings in more variables and stuff, and lets you calculate things that you don't really want. So instead, at every joint, there are multiple things connected, and you've numbered all the members. And so treat that joint like it's connected to the lowest numbered member at the joint. Okay, so that means, like, for example, at this pin joint at B, we're treating that pin like it's part of member 1 because, 1 and 2 are the two members attached. And I mentioned before that that's just total bookkeeping. You could do the highest numbered members. You could do the one that's drawn in front, whatever. If you have a system for it so that you only treat the joint like it's connected to one of those two, or one of those many, you can have more than two members connected at a joint. As long as that joint is part of only one of those members, everything will work fine. But practically speaking, the way I'm always going to do it is lowest numbered member. And so you probably want to do that too, just so our answers look the same. Yep.
You mentioned before we can only solve a problem if we got the correct number of equations. If you had 4 equations on body 1 and 2 equations on body 2, could you still solve that?
Well, because it's a rigid body, you can only get 3. But you never know for sure if you have the right number of equations, you know that things are looking good at that point, but it's always possible that some number of those equations are linear multiples of each other, and then that's kind of like those equations are degenerate and they don't help. So you never know for sure. Okay, so free body diagram of member 1. We had this reaction force RA. You could call that the force on member 1 by the ground, but we're never gonna isolate the ground, so that subscript notation just doesn't help there. So for reactions with the ground, I tend to just give it some other name. Then we have the weight force here, 196.2. And then here, the pin, which is part of member 1, the only thing it contacts is member 2. So we have the force on 1 by 2, and then that 600 Newton force. And I'm going to go from this to the table. I said that this was an equilateral triangle, so that means that these angles are 60 degrees. You can put your about point anywhere you want. I'll put it here. So the row vector for RA is 0. Force vector is RAX, RAY. Cross product is 0. And then MG, the lengths of these members are 1 meter, I think. So the midpoint here is at, it's halfway up that length. So 0.5 times cosine and sine is 60 degrees. So that's 0.5 times the unit vector, 0.5. Uh, 0.866. So this is 0.25, 0.433. And the weight force is 0, negative 196.22. And so you get, what's that, 20? Let me calculate that. 0.25. So negative 49.05. And then F12, that's just 1 times cosine and sine is 60 degrees. So that's 0.5, 0.866 for the row vector. The force is F12x, F12y. And so the cross product is 0.5 F12y minus 0.866 F12x. And then last is at 600 Newton force. That's at the same point, so it's the same row vector. 0.5, 0.866. The force is 600, 0. And so that cross product is negative 519.6. Any questions about that table? Okay, so we get 3 equations from this. I'm going to write it out for now, like carefully in the vector form and everything. But pretty soon I'm just going to start going straight to the equations. So this says RAX, RAY plus 0, negative 196.2 plus F12x, F12y plus 600, 0 is equal to zeros. So there's our first 2 equations. And then the moment equation, this is in 2D, so all we have is the z component of this equation. Negative 49.05 plus 0.5 F12y minus 0.866 F12X minus 519.6 equals 0. You can imagine it's pretty easy to just go straight from the table to these three equations, but I took this extra step. I'm going to write it out now as our first three equations. So we have RAX plus F12X is equal to negative 600. I'm going to get all the constants over to the other side so it's ready for reduced row echelon form. And then the second equation, RAY plus F12Y is equal to positive 196.2. And then the third equation says, I'm going to reorder these two, negative 0.866 F12X plus 0.5 F12Y is equal to 568.65. And generally, you know, you can't solve this as you go. You can't solve it until you do all of the rigid bodies. We can check what we have. So we have three equations. For variables, we have RA, so that's two variables. F12, so that's two variables. That's everything. So we have three equations, four variables. So there's no reason to believe we can solve for anything now. Just wait until the end and solve it as a system. Any questions about that first body? Okay, so now we're going to go to body 2. Down here we have a reaction RC from the ground. We have a weight of 196.2. And the pin is part of member 1. So that 600 Newton force isn't touching this. Okay, it's touching the pin. The only thing that's touching member 2 is the pin, which is part of member 1. So here we have the force on 2 by 1, or we've already defined this variable F12, so this is negative F12. Okay? Okay, I thought there was something else I wanted to say there, but so now choose an about point. I guess I'll choose this. Doesn't really matter. Bless you. So I'll start with RC. The row vector is 0. The force is RCX, RCY. Cross product is 0. The weight force, this is negative 0.25, positive 0.433. The weight force is 0, negative 196.2. And the cross product is positive 49.05. Okay. And then the force negative F12, that is at negative 0.5, positive 0.866 for a row vector. The force is negative F12x, negative F12y. So that's how that negative comes in there. Okay, we're multiplying the vector F12 by the negative 1. And so the cross product is 0.5 F12y plus 0.866 F12x. Any questions about that? One other thing with these forces, so I said, okay, that 600 Newton force is applied to that pin. And so that's how I chose to put it onto member 1. If it looks to you like, oh no, it looks like this is actually like not connected to that member, it's connected to this one, and you put it at that location on member 2, all your numbers eventually will come out the same at the end of the problem. So this whole thing about where you put the pin, it's all just about not double counting stuff. Okay. If you put this 600 at the pin, and then you put another 600 at 2, you're going to be calculating this thing as if this force was 1200 newtons. All right, so Newton's second law says RCX, RCY plus 0, negative 196.2 plus negative F12X, negative F12Y is equal to zeros. Is this okay with these guys talking like that, or is that distracting? Fine. Okay. I can live with it, I guess. So then the moment equation says 49.05. Oh. That fixes everything. So 49.05 plus 0.5 F12Y plus 0.866 F12X is equal to 0. And so this gives us our equations 4, 5, and 6. RCX minus F12X is equal to 0. Equation 5 says RCY minus F12Y is equal to 196.2. And equation 6 says, I'm going to reorder these, 0.866 F12X plus 0.5 F12Y is equal to negative 49.05. So we have 6 equations. Variables, we have the RA vector, the F12 vector, and the RC vector. So we have 6 variables. So this should work fine. Okay, so 1, 2, 6 variable.
center.
1, 2, 3, 4, 5, 6, 7. So here are 6 equations. And the variables are a x, are a y, f12x, f12y, rcx, rcy, and then the constants. And okay, so for the first equation, RAX's, we have 1. F12X's, we have 1. Constants, we have negative 600. For the second equation, this is going to be a common thing with the Newton's second law things. We're just shifting over these ones. And then the constant we have is 196.2. And then equation 3, F12X, we have negative 0.866. F12Y, we have 0.5. And for the constant, 568.65. Now for equation 4, RCX's, we have 1. F12X's, we have negative 1. And everything else is 0. For equation 5, RCY's, we have 1. F12Y's, we have negative 1. You can see that just shift over thing. Constants, positive 196.2. And then for the last equation, F12X's, we have 0.866. F12Y's, we have 0.5. Constants, we have negative 49.05. These matrices are always going to be pretty sparse like this. You know, a lot of zeros and not too many values. Can you all take a...
Can you just scroll back up a little bit?
Yeah. Okay, so
Oh, I see what I did.
what this says is, so if you think about the horizontal forces of RA and RC make sense. Those just have to fight against that 600 Newton force going to the right. Okay, what about the Y component forces? Is there a way to make sense out of that? Well, yeah, you can think that this 600 Newton force is trying to tip this structure over that way. And so this has to pull down on that to keep it from tipping over. This has to push up on that to keep it from tipping over. And that's why you get the negative Y there and the positive Y there. It's probably not worth spending too much time trying to make intuitive sense out of this. Like, I think, especially as this is a pretty simple one. As they get more complicated, you kind of lose your ability to have too much intuition about it. But that's what's going on there. I want to go back to the free body diagrams, though, because I want to point something out here that's a shame, but it's the reality. What if I had chosen this to be member 1 and this to be member 2? Okay, so then I put the 600 Newton force over on this one because it's the lower numbered member. Okay. these forces would look different. Okay, the reaction forces in this case would look the same, but the forces F1, 2, even when you flip the sign to account for, switching which body you're talking about, those numbers would look different. So what does it mean that the answers look the same in the end? That it gives you the same answers in the end. If we go back to the free bodies, so let's think back to member 1. What it says is we have this force of negative 243.36, negative 323.4. The downward force here. The force on 1 by 2 is negative 356.64, 519.6. And then we also have to remember there's that 600 Newton force. Okay. And now any forces that act at the same point are really just parts of the same force, right? So now I can rewrite this as negative 243.36, negative 323.4, 196.2, and this one is negative 356.64 plus 600 in the x direction. So 240, 43, yeah, 0.36, 519.6. Okay, and even though your numbers here would look different if you chose different numberings and stuff, once you got it into this form of representing all the external loads on that body, it would look the same if you did it right. The free body diagram on 2, we don't have to worry about that 600, so that one is a little more straightforward. So over here, we have negative 356.64, 715.8, we have the weight force of 196.2, and then over here we have the force on 2 by 1. That's the opposite of this, so that's 356.64, negative 519.6, was it? Okay. Any questions about that? That's kind of an important interpretation thing, and there will be problems where I'll ask you to draw out the final external loads on these bodies like that.
So I guess, and the takeaway from that is you just took what you calculated as the reaction loads and then you just added in everything else at those points?
Yeah, I mean, really all I did was I went back to the free body diagrams we'd already drawn and plugged in everything, and then any point where there are multiple force vectors happening at that point, just add those all together. Okay. Okay.
Joe's contribution.
Oh, yeah. I thought you were I thought he was just sitting there quietly and you're like, I'll bet he has a question. I know Joe. If I know Joe, I know this.
For point F1, 2, why does the force is not still equal around that point. It doesn't matter whether 600 is applied to one body or the other.
Why doesn't it matter? Like, why could you apply it to either body and it still has the same effect?
Yeah.
Yeah.
If the numbers aren't equal at that point on body one and body two.
Right. Well, I mean, the bodies. I mean, don't threaten me. I will do this problem again the other way. I will do that. I've been known to do that, right, Dan?
Yeah, that's right.
Let's do it, right? We got all the time in the world. Let's do that.
I mean,
And
I do trust that it.
Yeah,
it'll work.
but let's see it. I mean, it's cool to see it happen, I think, you know? Okay, well, let's do that next. Okay, so I don't know. People are split on this. Some people think this is the most boring thing you can possibly do, and other people think it's cool to see how it works, you know? So try to be the second kind of person right now. So what if we chose a different numbering? So this time I'm going to go 1 over here and 2 over here. And I guess I'll still go A, B, C. So free body diagram of member 1. We have RC. (196.2). Over here we have the force on 1 by 2. And the pin this time is part of this member, so we have the 600 Newton force. And I guess I'll choose this as the about point. So RC, row vector is 0. Force is RCX, RCY. Moment is 0. The weight force, that's negative 0.25, positive 0.433. Force vector is 0, negative 196.2. Cross product was positive 49.05. Then F12, that's at negative 0.5, 0.866. Force is F12X, F12Y. So the cross product is negative 0.5 F12Y minus 0.866 F12X. And then the 600 has the same row vector. The force is 600, 0. And so that comes out to be 5 something. Where was that? 519.6. So negative 519.6. And then the equations, I'll just jump right to the equations. So I'm adding up the x components first. RCX plus F12X is equal to, move the 600 to the other side, so is equal to negative 600. Equation 2, RCY plus F12Y is equal to positive 196.2. And equation 3 says negative 0.866 F12x minus 0.5 F12y is equal to positive 470.55. Okay, so that's a number we haven't seen yet, that moment produced by that 600 Newton force, because it's about a different point. Well, it's the moment produced, no, it's the sum of the moments produced by the 600 and the moment produced by the weight. That's why it's different here. 4 variables, so we can't solve it yet. Any questions about that first body? Okay, so now we'll go to the second body. We have RA 196.2. And then here we have the force on 2 by 1, or negative F12. I'll put the about point here. First RA, the moment, the row vector, the moment arm, is 0. Force RAX, RAY, cross product is 0. Then the weight force, the row vector is 0.25, 0.433. The force is 0, negative 196.2. Cross product is negative 49.05. And then negative F12. Row vector is 0.5, 0.866. Force vector is negative F12x, negative F12y. So the cross product is negative 0.5 F12y plus 0.866 F12x. Equation 4 says RAX minus F12x is equal to 0. Equation 5 says RAY minus F12y is equal to positive 196.2. And equation 6 says 0.866 F12x minus 0.5 F12y is equal to positive 49.05. And so now we can write this table, this augmented matrix. We have 6 equations. So that's 1, 2, 3, 4, 5, 6. And for variables, I'll go RAX, RAY, F12x, F12y, RCX, RCY, and the constant. So for the first equation, we got one of these, negative 600. For the second, one of these, positive 196.2. For the third one, negative 0.866. These are F12. Okay, negative 0.866, negative 0.5, and the constant is positive 470.55. Then for equation 4, RAX's, we have 1, F12X's, negative 1. For equation 5, RAY's, we have 1, F12Y's, we have negative 1. Force is positive 196.2. And then for the last equation, F12X's, we have 0.866. F12Y's, we have negative 0.5. Constant 49.05. Okay.